Now we turn to another problem that we'll be able to tackle with the dynamic programming paradigm, chain matrix multiplication. We are given a sequence of matrices of size m0 by m1, m1 by m2, and so forth, and we want to compute the product a1 through an efficiently. Note how the dimensions here are arranged so that such a product is always defined. The number of columns in one matrix always matches the number of rows in the next. First, recall that the product of an m by n matrix with an n by p matrix produces a matrix that is m by p, and that the cost of computing each entry is n. Each entry can be thought of as the dot product between the corresponding row of the first matrix and the corresponding column of the second. Both these vectors have n entries. In total, we have about n times p additions and as many multiplications. Next, recall that matrix multiplication is associative. Thus, as far as the answer goes, it doesn't matter whether I multiply a and b first, and then multiply that product by c, or if I multiply b and c first, and then multiply that product by a. The product of all these three will be the same, but the number of operations may not be. Let's see this with an example. We'll take matrices with these dimensions here and count the number of multiplications using both these strategies. If we multiply a and b first, then we spend 50 times 20 times 50 computing ab. This matrix will have 50 rows and 50 columns, so its product with c will take 50 times 50 times 1 for a total of 52,500. On the other hand, if we multiply b and c first, this costs 20 times 50 times 1. This produces a 20 by 1 matrix, and multiplying it by a costs 50 times 20 times 1 for a total of only 2,000. A big improvement. So it's important to be clever about which order we choose for multiplying these matrices.